In this video, I want to look at logarithmic differentiation. Logarithmic differentiation is a tool that we can use when differentiating. And so I'm going to just jump right into an example here. Let's find y prime given y is equal to the third root of 2x minus 1 over 3x plus 2 to the fourth power. So there's nothing preventing us from finding this derivative without logarithmic differentiation. We can do the chain rule with our cubed root. We can do the quotient rule of the inside of the function. Within that quotient rule, we'd have to use another chain rule. Absolutely possible. We could definitely do this just using those things, but it's going to take a little bit of time. It's going to get a little bit messy, but very doable, right? Remember with logarithms allow us to move around exponents. They allow us to break apart multiplication and division. It allows us to kind of avoid in a lot of ways the chain rule, the product rule, and the quotient rule. So what I'm going to do first is I'm going to take the log of both sides of this equation. We know that we're always allowed to do the same thing to both sides of an equation. So let's do it. And I'm using the natural log. You could use any log base, but natural log is as easy as anything else. It's easier than log because the derivative of the natural log function is just 1 over the inside of that. Alright, so now we have this expression. So before I actually go taking a derivative, let's see what we can do over here on the right hand side, because we can simplify a lot of things here. This cubed root, I can bring that exponent to the front as a 1/3. So I'd have 1/3 the natural log of 2x minus 1 over 3x plus 2 to the fourth. So notice we've just eliminated a chain rule that we would have to use. I continue working with this. With logs, I know that I can break apart division as subtraction. So I can write this as 1/3 natural log 2x minus 1 minus 1/3 Let's see if I can get my pen to write in this area. It's not responding. There we go. 1/3 times the natural log of 3x plus 2 to the fourth. And then that exponent can now be brought to the front. So we'd have the natural log of y equals 1/3 natural log of 2x minus 1 minus 4/3 natural log of 3x plus 2. So this does require our remembering the rules of logarithms. We have to remember our power rules, our product rules, and our quotient rules for logarithms. Now that we have this, notice it's all relatively simple. We have some very basic chain rules. Very, very basic though. So let's go ahead and take the derivative at this point. Now, on the right hand side, I've made myself a little bit more work because I have to use implicit differentiation. It's not just y, it's the natural log of y, which the derivative of that is 1 over y dy dx. On the right hand side, we have 1/3 as a constant multiple. And then the natural log, the derivative of that is 1 over the inside of that logarithm. Then I have to multiply that by the derivative of the inside, which will be 2. So that's the derivative for the first half, minus 4/3 times the derivative of the natural log 1 over the inside of the natural log times, 1 over the inside of the natural log times the derivative of the inside of it, which is just a 3. So we can do a little simplification here. And I'm also going to take that y and multiply it over to the right hand side. So I would have 2 over 3 times 2x minus 1 minus, the 3's will actually cancel, so I'd have 4 over 3x plus 2. Now one last thing I'm going to do here. We knew the initial function. And so unlike what we're doing other times with the implicit differentiation, a lot of times with implicit differentiation we just leave y inside the equation. We do that when we don't have a function of a y, when it's some sort of non-explicitly defined function, some implicitly defined function. But here we had the original equation for y, that was that cubed root of the 2x minus 1 over 3x plus 2 to the fourth. So I'm going to stick that back in for my y. Everything left in the parentheses stays. Like so. And there we have it. There would be the derivative of our function. And we've used logarithmic differentiation. So we didn't have to apply all those chain rules, the quotient rule. Was it a little bit of work up front to split up that log? Yes, it was, but then it turned the derivative into a very simple derivative. Do we have to do that? No, but it's a nice trick to have at our disposal. Are there times that we might have to use logarithmic differentiation? Well, we already saw to find the derivative of a non-e base exponential function, it was helpful. We could use it there. And so sometimes when we have those exponents that we just aren't quite sure what to do, if we can't work with those exponential functions, or if we have a composition of an exponential and a polynomial function, something like y equals x to the x, here logarithmic differentiation becomes a lot more important. We do not have a rule for this function. This is, like I said, a composition. We have a x in the base and an x in the variable. X in the base is like a polynomial, but an x in the variable is like an exponential function. So I'm kind of stuck here. So what I'm going to do is I want to get that exponent out of the exponent. I'm going to take the natural log of base sides. Oops. Base sides, there we go. And that allows me to take that x and write it in the front. I haven't taken a derivative yet, I've just rearranged the function. Now that I have it rearranged, I don't have any x's in the exponent. Now I can take the derivative. So I have 1 over y times y prime. I'm using the y prime rather than dy dx this time, just out of laziness. It makes no difference. And then over here on the right hand side, I have to use the chain rule. So I'm going to take x times the derivative of natural log of x, which is 1 over x, plus, and then we're going to have the the natural log of x stays. We take the derivative of x, which is just 1. So simplifying this, we'd have y prime is equal to y times, well, x times 1 over x is just 1, plus the natural log of x. And then plugging back in what my y was, that was x to the x times 1 plus the natural log of x. And there's our derivative. So again, on this one, we didn't have a choice. We cannot apply the power rule to it. We can't just say minus 1 because this has exponential properties. We can't apply the exponential property and say, oh, it's x times x to the x times the natural log of the base x. No, that's not true either. This was a more complex function. So logarithmic differentiation is very important to know how to do when we get to these more complex functions. For something like that first example, that was a fun little example to see how we can use it, and it made certain elements easier. We had to break apart the logs first, but it made the finding of the derivative easier. For something like this, it becomes very necessary. Let's do one more example like this. Let's take y is equal to the base of 2x squared plus 3 to the 5x minus 1. Again, here we have x's in the base and the exponent, so I'm going to take the natural log of base sides. When I take the natural log, the exponent can jump to the front, just speeding up our work a little bit, just bringing that down at the same time. Notice this exponent, this 2, does not get to move to the front because it is part of a larger expression. I can't break apart addition inside of logs. I can only break apart multiplication, division. I can only pull an exponent off when it's on the whole thing. So now I'm going to take the derivative of this. So the natural log of y is 1 over y prime. Here we have to use the product rule, so I'm going to leave the first, take the derivative of the second, and the derivative of the second would be 1 over 2x squared plus 3 times the derivative of the inside, which is 4x, actually, 4x. Okay, and then I'm going to add to that, I'm going to leave the natural log of 2x squared plus 3, and I'm going to take the derivative of the inside of the first function, the derivative of this thing, which is 5. I'm going to finish up with a little bit of cleanup, move that y over. Here, if we want to, we could distribute the x. We don't necessarily need to. I don't care that you do. So I'd have 4x times 5x minus 1 all over 2x squared plus 3 plus 5 natural log of 2x squared plus 3. I also need to rewrite that y in there. So remember that the y was the 2x squared plus 3. 2x squared plus 3 to the 5x minus 1. And then we have all the other stuff, so the 4x times 5x minus 1 over 2x squared plus 3. Don't need that parenthesis in the previous line, plus the 5 natural log 2x squared plus 3, and then close the opening parenthesis because this thing should be multiplied by that whole expression. And so there it is. There's our derivative.